Mike, without further ado, I'll let you get started and tell folks what's going on.
All right, thanks, Alan. So yeah, the title of the talk is Advancing Planetary Exploration, where no LiDAR has gone before. All of the LiDAR that you're about to see is actually from the Earth, but it is call it the proving ground for exploration techniques and what LiDAR can provide as far as data sets and information on other planets. So I'm Michael Zanetti, just started at NASA Marshall Space Flight Center about 6 months ago, and I've got 3 collaborators listed here. Dr. Antero Kukko in Finland, he's the head of mobile mapping and autonomous driving research, but he's actually one of the pioneers in backpack-mounted mobile LiDAR systems. And I hooked up with him, I think sometime in 2013, 2014, to do a tiny little impact crater survey in Estonia, and I'll show you that data a little bit later. And then the other 2 co-authors here are my former postdoc advisors, Dr. Catherine Nish and Dr. Gordon Azinski. Dr. Azinski is kind of a world-renowned expert in Arctic research and impact cratering, and Dr. Nish is a outer planets expert who's studying Titan. So we run the gamut of planetary science experts. So just a quick thing about me. There's a gratuitous shot of me outdoors, which means I'm an outdoorsy guy. But I did my PhD at Washington University in St. Louis in planetary science. And I'm a former postdoc at Western, or University of Western Ontario, which is where most of this data was collected from or with. I'm interested in the application of LiDAR scanning to scientific research and the geologic and geomorphologic processes and terrain mapping. So just a quick overview of the presentation to orient you as far as what I'm going to cover. Just briefly touch on what comparative planetology is and what are the applications for ground-based LiDAR systems, such as tripod-mounted systems and KLS, so kinematic LiDAR scanning, which we've kind of coined for backpack-mounted mobile scanning. And yeah, using the Earth as an analog to study other planets is kind of the quick and dirty explanation of comparative planetology. And I'll briefly touch on what I've been calling kind of the new geomorphologist toolbox, which is pairing LiDAR and UAV drone photography for really kind of focused research activities of kind of a small area. And one thing I probably won't touch on too much, but people in the audience might be interested in, is kind of getting the message out to academics as essentially as a market for those of you who are trying to sell these systems to people. I'm an academic, and I've come across these systems and find them really very interesting and incredibly useful for both providing context and for actual measurements. And just talking with colleagues, they're always wildly impressed with the data that we've collected and always ask me, well, how do I get it? And kind of getting the message out that LiDAR is not, doesn't have to be an airborne based system, which is incredibly expensive to either rent or use. And that the data sets aren't terribly difficult to work with themselves. So might be food for thought as a window into kind of non-industrial applications for LiDAR. I'll talk a little bit at the very end about LiDAR for planetary applications, and then if these slides are made available, I'm not sure if they will be, but there are a couple links for the articles that I wrote there. So what is comparative planetology? It's essentially the study of natural processes and systems on and between multiple planetary bodies. We have to kind of remember sometimes that the Earth is a planet, so we can apply what we learn on Earth to other planets that we observe through mostly remote sensing techniques. And this involves geology, geomorphology, hydrology, atmospheric physics, pretty much anything that we can observe on Earth and then apply to other planets. I've shown here just a kind of a snippet of impact craters because this is what most of my research involves. But on the far left there, you see Meteor Crater here in Arizona in the United States, which is one of the test beds for testing theories about impact cratering and how we can use a place like Meteor Crater to better understand a very common but seldom process in the solar system, which is impact cratering. Is when a big asteroid slams into the ground, super high energy. And we would apply that to, well, how do we learn about impact craters on Mars and what are the small differences or subtle differences there? And then how we apply that to the Moon and Mercury as impact craters get either larger or more common or different terrain, that kind of stuff. But there's a need for ground truthing observations. So that's where most of comparative planetology comes in. And so we'll jump right into some of the field sites that we've used LIDAR at. This is an image of our field site, or one of our field sites on Axel Heiberg Island in Nunavut, Canada. So this is quite far north, about 78 degrees north latitude, where the main goal here was to study both terrestrial processes and geology of kind of an exotic terrain with interesting geology. Axel Heiberg is known for salt diapirism, which is interesting for the petroleum industry because oil is often associated with salt diapirs and things like that. And so we went there to study that terrestrial process and also compare the high Arctic to Martian terrain. We find that there's a lot of similarities to the cold and relatively dry climate of the high Arctic to the very cold and very dry terrain that is on Mars. And so in this picture, you see little rivulets and gullies and things like that on the slopes of the mountains. Those are very common on Mars, and if we can study them better in similar terrain on Earth, we can get an idea of that process and the amount of water and things like that necessary on other planets. So, and I neglected or forgot to mention this at the top of the presentation, but Teledyne is sponsoring this series, which is incredibly valuable. I've called into a couple of these webinars in the past and learned quite a lot. While we were in Canada, we wrote a tiny little research grant with the Canadian Natural Resources Canada organization to get funding to essentially pay for my plane ticket up north. And Teledyne Optech generously agreed to loan us both a Maverick system, which is their portable LiDAR and photogrammetry system, and a Polaris system, which is their newer version, their new tripod mounted system. And what we did as part of that grant is built a backpack rig for the Maverick in order for us to kind of walk around and study ground patterns and things like that. We had considered in the past trying to do LiDAR-based drone scanning, but in the Arctic, the weather is quite unforgiving and most of the time quite unfavorable. Certainly for flying expensive equipment on expensive drones. Usually have high winds, and we were always very frightened to put anything in the air for fear of losing it. So the main idea of going to the Arctic was to study ground surface patterns. So in the high Arctic, there's very little vegetation, and there's permafrost. And there are yearly cycles in permafrost freezing and thawing. And that freezing and thawing effect acts to create kind of these really wild and crazy patterns in the ground through cryoturbation and frost heaving. So this is all similar if you live in anywhere in cold climates to what happens to your driveway with potholes. Water will infiltrate a crack and freeze. There's a volume expansion for freezing water, and that'll kind of wedge things open. And if you do that, over multiple cycles, over many years, you'll actually end up sorting different size stones and also creating kind of wild and crazy patterns. So on the right here, you see a subset of what are called polygonal pattern ground. Each of these little squares there are fractures in the ground that contain a lens or a wedge of ice. And that wedge of ice, as it goes through freeze thaw, will continually open and create this pattern. So one of the other things that we were doing while in Axel Heiberg was testing this kind of new geomorphologist toolbox idea, which is what is the best way to collect site-specific ultra-high resolution data for remote areas. So you can get 60 centimeter per pixel satellite imagery for these areas, but if you fly a drone, even a simple DJI, Phantom drone, if you have a specific subset in mind or a specific small area in mind, you can map that with the drone photography and then also get ultra high resolution topography using the lidar systems. And so that combination gives you essentially your ultra high resolution base map for kind of whatever studies you wanted to do. I'll also note here in the middle of this, the picture in the middle of the screen here, there's a big white patch in the background there, and actually you'll see our tents even farther back in there. That's actually not snow. Despite being in the Arctic, we were mostly with relatively snow-free areas. That white patch there is actually a large salt deposit. There's a spring. I wouldn't call it fresh water because it's all salty water coming through these salt diapirs that are in the region. But as it comes out, that salt precipitates and crystallizes and forms, kind of these large deposits. And we were using both the aerial photography and the lidar to map those deposits for year-on-year change detection, which is another kind of very powerful tool for lidar. Yeah, next. And we were also kind of walking around an awful lot with the Maverick system. I'm sure. So we basically used the Maverick system essentially as much as possible. We were actually most of the time operating outside of the call it the design constraints for the Maverick, and it held up quite well. We were operating probably about 10 degrees Celsius below their minimum operating temperature, and we're still collecting pretty excellent data, kind of at the order of about 15 centimeter per pixel digital elevation models. What you see us doing here is essentially walking up a very steep-sided gully that was etched into one of these salt diapirs. And we were doing this in order to understand gully morphology. So how does this gully form and incise into the ground? It seems kind of straightforward. Rain falls or snow melts and it etches a gully, but there's a large amount of debris component and things like that to these systems. And we can compare what we find on Earth to gully systems on Mars, which form quite often. And we can understand better the rate of formation and how these form on Earth in different types of terrain, and how that different type of terrain will actually affect the end morphology, and then use that to infer physical properties of the ground on Mars. So in addition to Devon Island, we also went, or in addition to Axel Heiberg Island, we also went to Devon Island in Canada, which is the largest uninhabited island in the world. And we had a really high energy campaign here. Devon Island is home to the Houghton impact structure, which is this kind of circular feature with all the stars on it that you see in the image on the right. This is about a 24-kilometer diameter impact crater, and this is, one of the best places in the world to study both the impact cratering process and for comparisons to Mars, because the climate on Devon Island is reasonably similar to the current climate on Mars. And what better place to do it than in an impact structure for comparisons to Mars. So each of these little stars that you see here are areas that we mapped with a different system that I'll introduce on the next slide, which is another backpack mounted. Well, this is the system. We'll come to this in a second if we go back to the last slide. Well, so we have a backpack mounted system that we that is essentially a prototype or a custom built rig by Antero Kukko in Finland, and we deployed that system about 35 times over about 2 weeks. So about twice a day we were out there mapping the ground. One of the primary reasons to do this was to map out 50 meter by 50 meter grids at as high a resolution as kind of physically possible. And what we were trying to do is understand in ultra high resolution the surface roughness of these areas to compare to radar data. I don't show any of the radar data because it is quite complicated, but essentially if we can understand the surface roughness, we can understand radar backscatter. And our approach here was to map out and walk essentially back and forth over these small little grids in order to capture the surface roughness at more than a few tens of radar pixels. So this is the prototype rig, the Akka R3. Akka, loosely translated in Finnish, is kind of the old hag, which after carrying around an 18 kilogram, 40-pound system for a few hours, you'll understand why we called it the old hag. But it is essentially a Regal Vux 1HA scanner hooked up to a UIMU LCI internal measurement system, or inertial measurement unit. And a GPS antenna. And so this system gave us kind of 1 million points a second and up to 250 lines a second with very high precision and excellent range. So essentially, as we walked over the ground, within about 20 meters on each side of the scanner, we were getting something like 5,000 or more points per square meter. So if there are technical folks in the audience, this is an incredibly high resolution system. Does require quite a little bit of post-processing in order to match data together and create clean point clouds, but we had incredible success with this. And features as small as 1 centimeter are kind of clearly defined. So if you ever wanted to have a graduate student count rocks and boulders, boy, we have the ability now. And so this is a subsample of the data that we've collected using the R3 KLS scanner. Like I said, about 5,000 points per square meter within 20 to 30 meters of the scanner. What you see in the left is a colorful image. This is color coded essentially by each minute of data collection. And as you walk over the ground back and forth, you'll catch, you'll cover features from different angles And this really minimizes the number of shadows that you'll see. And this is the same technique that we used for the Maverick system. Yeah, I'm just showing the data, the point cloud data here for the R3. But what you can see from the data here is that we get, an incredible rich data set that's essentially got more detail than we can ever use, or at least right now. On the right, you'll see some polar bear footprints that we came across while hiking around in the Arctic. Yeah, in the greens and purples and blues, those are the polar bear footprints. If you note just to the right of those, that's a man's footprint. This is essentially dried mud. So the polar bear wasn't close by. We reckon he was about 6 months past. But you can see the lines of the scanner, as it's scanning at 250 lines a second, creates lines. And as you're walking along, some of those lines will bunch up. So the data set is not kind of evenly distributed, but you can kind of take care of that in post-processing. But I will note that, if you notice the man's footprints there, we're capturing incredibly fine topographic differences. That's probably less than a centimeter of elevation between, surrounding terrain and what ends up being pressed into the ground by the foot. The polar bear is significantly heavier than the man's footprint, so it's sunk in a little bit deeper. So what you see here are a couple of different types, or a couple of different examples from different types of geologic units in the Arctic. So on the left, you'll see fluvial deposits. In the middle, you'll see something called an impact melt breccia. This is a type of rock that is specific to the Houghton impact structure. And on the right is Allen Bay, which is essentially a limestone sandstone unit. Each of the big digital elevation models in below are the full 50 meter by 50 meter grids that we essentially captured. Now we had the scanner running essentially all the time, and we're collecting data as we either did walking traverses or even tested it as scanning while on ATVs, because that was the main way to get around in the Arctic. But what you see are, essentially three different types of how the ground responds differently to this freeze-thaw process. And so in the fluvial deposits, you get these long fractures. These are ice wedges, but you also get this kind of mottled texture, circular pattern ground, and that's stone circles. And I'll talk a little bit about that in a second. But yeah, each different type of geologic unit in the Arctic seems to respond uniquely to the freeze-thaw process. And because we now have 35 different places where we've got this kind of standardized ultra-high resolution data, we're now proceeding to understand better that surface process. So this is just zooming in to a 10 meter by 10 meter box of the same images that you just saw. And you'll see here where some of the differences in kind of that pattern. I'll point out that the vertical exaggeration, or the vertical scale bars here, in most of these cases are just absolutely mind-blowing as far as the vertical relief that we can capture. So in the fluvial deposits on the left, we're only looking at about 40 centimeters of relief, so 18 inches between the deepest blues and the highest reds. And in the center image, in this impact melt breccia, which is a little bit spongy, when you walk on it, we're only looking at 20 centimeters difference, so 10 inches. And if you look very closely in the middle of that image, you'll actually see footprints from the operator. Footprints are actually kind of common because we're scanning behind us with this system, and so we can track where we went. So I did want to sneak some science into here, or at least some geomorphology for folks who are kind of baffled by this these kind of crazy patterns. So circles, polygons, and stripes are formed through this freeze-thaw process, and this ends up sorting fine material and stones through cryoturbation. As kind of water infiltrates underneath a rock and then freezes it, that it'll actually force the rock up. And what'll end up happening is that fine material, so sands and whatnot, will fall in behind that rock. And over time, and it's somewhat mysterious still, that'll force rocks kind of together and create these large stone circles. And those stone circles are, they've been studied for the past 100 years or so, but what this ultra high resolution LiDAR is now allowing us to do is understand this process over much larger areas than kind of ever before. These are not these are not rare features. Throughout the Arctic, almost every surface is patterned in some way because of the permafrost. But studies in the past have kind of been limited to, understanding individual or very small areas of these stone circles, just because of the amount of field time it takes to collect data and make tape measurements, essentially. What we can do now, given the precision and accuracy of these systems, is cover essentially acres and understand how these systems are working together over, tiny variations in vertical elevation, and understand why some areas create large stone circles and some create smaller circles, and how this is related to, call it, micro topographic differences in the drainage or nature of the permafrost. Now, this seems a bit esoteric, but as we understand these permafrost terrains better using this LiDAR, we can actually understand how to build systems, build buildings and other features like pipelines and that in permafrost terrain. And so, yeah, these LiDAR systems are going to be incredibly important for both the fundamental research of permafrost terrain, and then the geotechnical aspects of how these terrains are moving and shaping over time. Because these are essentially slow, but not as slow as you think processes. Stone circles can develop either over thousands of years, or in some types of terrain, even a small disturbance like deer running through a kind of a soggy valley will actually create pattern ground within about 10 years. And so if that type of subtle thermal disturbance will create crazy patterns within 10 years, you have to understand what happens when you put a pipeline through one of these areas, right? And so I mentioned that, we can now use these types of systems to cover essentially acres. So what you see here is a 500 meter by 400 meter essentially mountain that we mapped in about 2 hours hiking around. The effective resolution of the DEM on this is about 5 centimeters per pixel over about 3 acres. Took us about 2 hours to do of just wandering around. And the blue line there is essentially the path that we walked. We can cover highs and lows and get close to cliff faces for extra detail to do geologic analyses and understand patterns over large areas. The cloud here is about 4 billion points. And when you look at something like this, you would say, well, why not just use an airborne drone? And it goes back to what I mentioned earlier with essentially weather conditions, and fear actually plays a lot into it. The Regal system is about 100K. or $100,000. A drone that can support that is probably another 100, 150 plus IMUs. You'd be hard pressed to get academics to put $250,000 in the air in bad weather. And so having a backpack mounted system like this, we can scan in essentially any weather. We were out for 2 weeks in bad weather, scanning essentially every day. So in addition to the KLS system, the ACA R3, we did a lot of tripod scans using the Teledyne Optech Polaris. So this was, we had used the Maverick on Axel Heiberg, which is a different place. And we took the Polaris to Devon Island in order to study a lot of these gullies, again, for comparison to Mars, and just to understand them in different terrains in the Arctic. So one of the things that we're really interested in using the Polaris for is change detection. So Gordon Azinski, co-author on this paper, or on this research, has been going to essentially this site for the last decade or more, and has collected slope information using the older Optech ILRIS data, essentially yearly going back for 15 years. And now that we've got the Polaris as another long-range scanning opportunity, we can continue that in higher resolution and in a lot kind of faster data collection method. And so we're in the process right now of understanding how have these systems changed over the last decade, and we can use that information to understand, how a similar system on Mars might evolve over short timescales, like a decade or even longer. And so linking back to Mars geomorphology, the two images that you see here on the right are actually Mars data. So if you picture in your mind what you just saw from the Polaris data, all those gully systems operating in an impact crater, this is what we see on Mars. And so all of these systems are clearly, or most of these systems are clearly fluvially related, which means running liquid water on Mars. So there's implications for habitability with that, and also resource utilization. Water tends to make really good rocket fuel. And so understanding where we find water on Mars is a really important topic. So that's the top picture of gullies in an impact crater wall. And in the bottom, these are the same types of patterns that you saw on both Axel Heiberg and Devon Island. So there are clearly periglacial permafrost processes acting on Mars that are creating similar patterns, but at a completely different scale. These are much, much larger features. And so for us to understand how do you make such similar looking, but order of magnitude larger features, how is that different, and how is the terrain different to allow that? And so that's what this ground truthing using the lidar is actually doing for us. So we'll put aside the Arctic field work for a second and talk about some really interesting volcanic features. So with the NASA Solar System Exploration Research Virtual Institute Field Investigations to Enable Solar System Science and Exploration Team, so the SURVEY-FINESS, I gotta love NASA acronyms. The NASA SURVEY-FINESS team was a kind of a consortium of about 30 scientists that descended on Craters of the Moon National Park in northern Idaho to better understand the geology of that region, which are some of the youngest lava flows in the United States. They're about 2,000 years old, but with the main goal of understanding exploration techniques and Given a limited amount of time in an area, how do you maximize the scientific return and exploration of that area? And so a whole bunch of different systems were being used. UAV drone data was collected. TLS tripod scans were collected. We used the R3 KLS backpack scanner for for a lot of studies. Geophysical data was collected, rock samples and things like that. And it was essentially how do you best explore a rugged terrain like craters of the moon, with the anticipation of using that to better study the moon and Mars. So if we look at some of the data that we collected on lava flows might be a little bit more intuitive for people in the audience, because they might have gone to a national park before and actually stood on lava, whereas periglacial terrain like pattern grounds, that's a little bit more, call it esoteric. But what you see here on the left is a ground image of what essentially a pohoihoi or smooth flowing lava flow looks like. And on the right, this is the data that we collected using the R3. So again, if you look at the elevation difference between the lows and the highs, most of the highs here are actually little bushes that are in the scene there. But we can understand to an ultra fine level the morphology of these lava flows and how they evolved, and then using that to understand flow dynamics and the evolution of flows, and back out even more technical data like the rheology of these flows using remote sensing. So if you have a system like a lidar with ultra high resolution, but you don't have an ability to, let's say, take samples to understand the composition, sometimes you can back out compositional properties just from the morphology and the rheology and doing some math. And so this is another example of some of the data that we collected. And again, compared to, this is a USGS photo from, I think, one of the most recent volcanic eruptions on Hawaii. The quality of the data that we're now collecting is such that we can see tiny little differences, pressure ridges, striations, and understand the flow mechanics better than ever before. And again, over huge areas that wouldn't have been, call it, easy to do before. But yeah, if you look at how this lava flows and how the surface of the lava kind of squelches up into these curvilinear patterns, that gets frozen or essentially solidifies. And when we go over it with the LiDAR, we can fully capture that. What's interesting beyond just the morphology is the effect that this has on remote sensing data, like short band radar. So one of the aspects of this study is we've also looked at airborne and satellite radar data over this terrain to understand the backscatter of the remote sensing radar. And using this ultra high resolution LiDAR, we can understand the surface roughness at essentially the scale of the radar. So we really understand better than ever before the backscatter. And understand just subtle differences in orientation. So these curvilinear features that you see on the right, those actually have an enhanced signal in the radar because they're at the proper size and in the proper orientation to create a bit of a hotspot for radar. So yeah, back to this catalog of amazing features that we've been able to scan. This is a spatter cone. So up in the upper right, you see what this feature looks like on the ground. This is about 30 meters tall. And this is call it a mini volcano. This is essentially formed by splattering and small explosions of blobs and blebs of lava that kind of build up over time to create, essentially a mini volcano. And what we were able to do with the backpack mounted system is essentially just walk around this and completely characterize the morphology of these features. So in the image below, you see this is color coded by each minute of data collection. So essentially it took us about 17 minutes to walk around. And if you go to the next slide, you'll see that we can then use that data to understand better some experimental work that we're doing. So if we just take the morphology data, we can create cross sections and understand the morphology of these features, and then then using that data, better understand how these features were created. So what you see on the right are a series of images from the University of Syracuse lava project. They essentially have a gigantic furnace outside that they melt a lot of rocks in and do volcanology experiments occasionally. And what we were doing here is essentially trying to, fabricate these lava blebs to understand cooling processes and how they essentially weld themselves together to create this volcano. And at the same time, we can also understand, how those curvilinear features are formed, and cooling rates and rheology of these flows based on different compositions and different temperatures. One of the other really interesting, cool things that we were able to do is map lava tubes. These are essentially subterranean rivers of lava, where lava was transported during some of these more effusive flows. The data that you see in the middle is from Brent Gary. He's at the Goddard Space Flight Center. And he's been studying a place called Indian Tunnel, which is at Craters of the Moon, for a couple of years. And he's been doing this with the survey team using tripod mounted scans. And what you see are about 50 different locations where he's scanned using the tripods in order to create this kind of incredible three-dimensional tube of, or three-dimensional reconstruction of this lava tube, and better understand, how the lava flowed. You'll notice in that image that there are a couple of call it skylights. This is areas where the roof of the tunnel has collapsed and allows sunlight access. And while we were there using the backpack system, which still is dependent on GPS, we decided to test whether or not we could use the backpack system underground and periodically pick up a GPS signal from these skylights. And we had great success. So if you look at the data that was collected using 50 scans, this took probably more than 2 weeks of kind of dedicated labor. Anybody who's done tripod scans knows that you stand around a lot. And if you hit next, we were essentially able to collect similar or comparable quality data in minutes. So what you see here is about a 50 meter or 80 meter section that was scanned in about 3 minutes. And this is between two of those skylights. We were able to collect the whole thing in about 17 or 20 minutes. And so that enormous difference in collection time means that your field activity can be better spent doing other things than standing next to a tripod. And then we can use that data in combination with other data sets like geophysical data. What you see on the right here is a combination of data sets. This is lidar topography draped over with magnetic data. So if you look at the left there, you see two of my colleagues walking around collecting magnetometry data, and this is looking at subtle variations of the magnetic field. And there are subtle variations as you walk over a void space. And So in the rainbow data there, you can see that the trace of this lava tube is quite easily seen in magnetic data. It's that blue streak that runs down through the center. And then using that data and the point cloud data, we can then do 3D reconstructions of the tube and its relation to the geophysical data. And we also did this for gravimetry, which is subtle variations in the gravity field because of a void space. But this is call it a better looking data set than that one. And I did promise, this is one of the oldest projects that Antero and I have been working together on. This is a tiny impact crater that happened about 3,600 years ago, so 3,600 years before the current era. And this is a 100-meter diameter impact crater that happened on an island in Estonia. So this is actually essentially call it Bronze Age impact that happened, and probably freaked out all the people that were living there at the time. So my job here was to survey this using a TLS system, so tripod system, and it took me about 40 scans and about 3 days. And then the post-processing to remove all the trees took even longer than that. Whereas a previous version of the KLS was able to do this in about 30 minutes. And that enormous amount of difference in time, it was really what woke me up to the power of mobile scanning as a tool. And so we're using this type of data for crater shape to understand the impact cratering process. And just as a fun little story, I mentioned this is a Bronze Age crater. It was an iron impactor. So an iron asteroid fell out of the sky, hit the ground really hard, created a small forest fire. But as everything settled down, those Bronze Age people went back and picked up fragments of the meteorite that didn't completely melt or vaporize, and used those to make stone tool or to make metal tools. And some of the artifacts that you find in this area can actually be traced to the same meteoritic metal that formed this impact crater. So just to summarize a scientist or user perspective on this ultra high resolution LiDAR data, mobile LiDAR mapping and surveying products are really pushing scientists like me to figure out just ways to use the data to its fullest extent. We've never really been at this point where we've essentially got better morphology than we've ever had before. How do we use it? And how do we adapt our models to be able to use such high resolution data? The question is, how much resolution is needed? Well, always more, because we are learning things that we never really thought about before. Like I mentioned, this microtopographic difference in pattern ground. So don't worry, give us more data, we'll catch up. Some measurements can only practically be done with LiDAR, either backpack or UAV systems. So these large area surface roughness analyses for radar studies, that's a really novel use. And you can't get that level of detail or resolution or confidence in your data from photogrammetry. And so new observations relationships are always being discovered because of this level of resolution. And I mentioned a couple of examples from that. So this will close out my talk with we talked a lot about LiDAR on Earth. What do we have for LiDAR data for other planets? So satellite-based laser altimeters have explored the Moon, Mars, and Mercury, and also asteroids right now, and even, so yeah, like the asteroids of Ceres and Vesta, and even some smaller ones, where a mission called OSIRIS-REx is currently mapping to 7 centimeter per pixel, or 7 centimeter spot spacing of a small asteroid called Bennu. But so these are creating essentially, amazing topographic maps of the entire planets, but these are still relatively low resolution, given, compared to what you could get from the ground over smaller areas. And if you're interested in this type of stuff, there's a reference there. So what about ground-based lidars on other planets? There has yet to be a ground-based topographic lidar collected from the surface. There have been some lidars that are atmospheric lidars, but they're pointing the wrong direction from my perspective, that are studying, the atmospheric column of Mars. But there is some currently focused development for lidar for planetary exploration, but these are tend to be mostly entry, descent, and landing systems for automated hazard avoidance. Kind of as your spacecraft comes into the surface, you're using both lidar and radar in order to characterize the surface for automated landing. And then there's also some work with atmospheric lidars, and those are the ones that are also being developed. Again, satellite-based, looking through the atmosphere of Mars and Venus. There are navigational lidars for rovers that are being developed. I know this is being done in Canada and the US and even in Europe. And so there's the question of dual use navigation and science possibilities. So, so if we talk about the challenges of LIDAR in terms of planetary exploration, I'm a LIDAR geek. I really think that LIDAR provides a level of detail and accuracy that you don't get from photogrammetry. But they are tremendously kind of volume heavy. So data volumes for science would be enormous, right? So if you could imagine a rover traversing a surface, kind of constantly scanning, you're going to collect, gigabytes or terabytes of data, and getting that data back to Earth is challenging given kind of current bandwidths for data communication. And I make the note here that data volumes for science are the ones that are going to be problematic, right? Navigation, you can essentially collect your LiDAR data, use it for your hazard avoidance, and then just chuck it away. So yeah, one of the big challenges, how do you get that data back to Earth? So optical communication technology for high data transfer for the moon is a possibility. It's actually been tested recently for spacecraft communication. But optical communication for other planets is challenging. Perhaps ground to satellite is possible, but satellite back to Earth using optical communication is still in its infancy, call it. And then other planets are essentially GPS denied environments. We don't have GPS around other planets. So how do you get these systems to operate using either just a IMU or some other system? And then there's the kind of harsh radiation environments that you might be dealing with in these environments. So you would have to make a far more robust system, perhaps, than what you would be designing for Earth. And then I list photogrammetry here as a challenge because the question does LiDAR provide enough benefit in terms of the accuracy and resolution compared to that data volume? And so that's currently the Mars rovers use photogrammetry for most of their navigation because it's just less data intense. And so this is just my final slide on NASA's interest in LiDAR technology, and I won't talk too much about this because there are a bunch of other centers that are far more involved in this than I am. But active optical measurement techniques are critical for the future future NASA Earth planetary science exploration and aeronautics measurements. That's from some of these resources and references below. The science decadal surveys recommend a number of missions requiring active optical systems to meet the science measurement objectives over the next decade. And so there are active calls out there for LiDAR systems, both satellite-based and ground-based. And so if you are at a company that's interested in this type of stuff, check out some of these resources and references. And with that, I'll say thank you to LiDAR Magazine and Teledyne Optech for sponsoring both the webinar series and helping us with our fieldwork in the Canadian High-Arctic. That was incredibly generous of them, and we owe them a lot of thanks.
Thank you, Mike. We really appreciate it and appreciate your accessibility with this. We've got a lot of questions that I believe we haven't left a lot of time for Q&A, so we'll follow up directly or send Mike's. I believe we're going to share your email address or a method of contacting you within the follow-up. So you all receive a recording slide deck. We'll share the slide deck as long as that's cleared or vetted.
Yeah, it should be. I'll double check, but yeah.
Yeah, slides.
Oh, I apologize for going so long.
It's completely okay. There's a lot of questions, Mike, relating to sharing the data. Quite a bit of technical stuff. You could address a couple, but I think a lot of these are best addressed directly with you. Please, if you have questions now, ask them. We'll just follow up after. You might get a direct email or who knows, maybe even a call from Mike. I don't want to promise anything, but again, thank you so much, Mike, for your accessibility, for making all this available. It's great to have it in the magazine, but we really like making it available in this manner. So quickly, maybe address just a couple quick, a couple of the questions from the top. What is finesse again? Can you explain finesse? You addressed this in the last magazine.
Yeah, finesse is a group of scientists. So it's essentially just the acronym that we've assigned our program for study of the Craters of the Moon National Park. And so it's I've got to remind myself what it is. Just field investigations to enable solar system science and exploration. And so that is, again, just the acronym for the group of scientists and the name of that program.
Gotcha. Are you able to share some of the grids that you showcased today? Can you share those with folks, or I guess on a case-by-case basis? Or
it would be case-by-case and kind of, if you have something wild and exotic that you want to try to do with the data, I'd be happy to share it with you. These are active areas of research, so we'd have to know. We don't want to double up or steal some graduate student thesis, but.
Understood. We'll follow up on most of what we've got. So
I've listed my email address here in the chat room. If you want to talk LiDAR or ask questions about the data, feel free to email me, and then I can also provide any other input from my perspective.
Absolutely. No, thank you so much, Mike. And hey, thanks to everyone that took time to attend today. We appreciate it and look for the follow-up shortly.
Yeah, I appreciate it. Thank you, guys.
Have a good day.